So the topic I wanted to discuss today is, some sense, what linear algebra was invented for, which is solving linear equations. Although we'll go a little bit beyond kind of the basic methods for solving and see some sort of methods for solving them approximately but fast, using the knowledge we have developed so far in terms of eigenvalues, singular values, and inner products, etc. So, but before we go there, let's just recall the way of solving linear equations that we've all used previously. I guess it's let's say a general system of linear equations can be written as A times x plus b, where x is a vector of indeterminates or variables which you need to solve for. You can think of them as a column vector. A is a matrix of coefficients and b is whatever are the right hand sides of these equations. And let's just consider a toy example, which is the simple system of equations which I cooked up. Okay, and just to sort of recall how one would solve this equation, maybe you'd subtract the first equation from others. I mean, again, you can sort of eliminate any variables, but here I'm going to eliminate x by subtracting the first equation from the second one, and also subtracting 2 times the first equation from the third one. So I get a system where the first equation is as such. For the second equation, I get and for the third one, again, I eliminate x, so I get please do check my calculations just to make sure I'm not messing something up. Okay, and now maybe we can eliminate y from another equation. So I'll leave the first one untouched. I'll leave the second one untouched, and subtract the second one from the third one. Okay, and here I can kind of rewrite this equation in a nicer form, which is z is equal to 2. This kind of divide both sides by -3, and then I can go backwards. So once maybe it sort of looks like z is equal to z. Okay, hopefully that's a little clear. And then I can go backwards. Once I know the value of this, I can plug it into the previous equation. I get the value for y, and I can plug that into the previous equation, the values of y and z, and I get x is equal to 7. Okay. So that's a sort of way of solving linear equations that we are all familiar with. And just to recap it, or sort of write it in a different way, we can think of a matrix where we have the matrix A with an extra column, which is all the entries of B. So just B appended as a column vector. In this case, we would have the matrix 1, 1, 1, 0, 1, 2, 3, 15, and 2, 3, 1, 19. What I did in the next step was kind of subtracted the first row of this matrix from the other rows with some multipliers. So I obtained zeros. And then I did the same thing with the second row subtracted from the other rows. And subtracted, I got really a row which was -3 and -6, but then I divided this row by -3 to get this row 1 equal to 2. Okay. This is a procedure you're probably familiar with. You've seen this is referred to as Gaussian elimination. And you get this matrix in a convenient form that you can start from below and sort of solve for one variable, plug it back in an upper equation, solve for other variables, and so on. Anyone has sort of a question about this computation? Okay, so let's just sort of recap what we did in a slightly more formal way. So we arrived at this matrix, which we obtained by doing these operations. And it had a few properties which helped us solve this linear equation. Let me just capture those properties. And this is this particular kind of matrix is said to be in row-reduced form. And so in general, a matrix is in row-reduced form. It has the following properties. The first non-zero entry of each row is 1. And I mean, if not, we can just multiply or divide that row by something so that it becomes 1. And then this, if you think of each row as representing a linear equation with the right-hand side, it's just multiplying a linear equation. If you multiply it by a non-zero number, it's still a valid equation, and that's an operation you can do. So, and this is also called the leading entry. And then this sort of fact that when we substitute a variable, we can solve for other variables is given by the fact that if you have a non-zero entry in a certain row, then the stuff below it, to the left of it, and sort of is so the rectangle for which this is the top right corner is contained, sort of is only filled with zeros. And this is just made formal that if you have any row which is below it or any column which is to the left of it, then the entry is 0, except of course when you're looking at this specific entry, which is 1. And finally, yeah, this didn't happen in our situation, but any rows which contains all zeros are below all the non-zero rows. So I mean, those are equations which are not interesting because all coefficients are 0. If the right-hand side is non-zero, you immediately know that you can't solve this system of equations because, well, you can't multiply a bunch of variables by 0 and add up to something non-zero. But otherwise, yeah, you can discard them. The fact that you obtained 0 essentially means that these equations were basically linear combinations of other equations, or they are redundant. And so you can just use the other equations to solve for the variables. And if we go back to what we did to get our matrix in this form, one of the sum of the operations we did were maybe you subtracted or added some scalar multiple of one row to another row. Maybe you multiplied a row by some scalar. And finally, something which we did not need to do here, but if you want to bring the 0 row at the bottom or arrange them in this particular format with the leading entry having kind of the rectangle to the sort of left and below it being 0, you may need to exchange 2 rows. And that just means that instead of calling something in the first equation, something else the second equation, you're just changing the order and calling the second equation the first one. And that doesn't, of course, change the solution to those equations. So, and so the method we just saw for solving linear equations, and this is something which you've probably seen, this is just a reminder, solving method for solving linear equations where you just sort of subtract linear equations, eliminate variables until you have a convenient form, can be stated in this way, that you are given a matrix which has the coefficients to your equations and the right hand side to your equations. You do all these operations, which again, subtracting one equation from another, or adding one equation to the other, multiplying a equation by a non-zero number, or changing the order of the equations doesn't really change the solution. And viewing this in the matrix form, we do these operations until our matrix is in the row reduced form. And these operations are referred to as elementary row operations. And once you bring the matrix in the row reduced form, you can solve by kind of first solving the last equation, then substituting the value up and up and up all the way until you solve for all the variables. Okay, or you can get a sort of a zero row with a non-zero right-hand side, and you can decide that the equations don't have a solution. So this is the method we are familiar with, and I'm just formalizing it. These are using this kind of elementary row operations, and the method itself is referred to as Gaussian elimination. Any questions about this? Okay, so I mean, there are a couple of things to check out, sort of check beyond solving linear equations. This is a nice method for proving things. And so one thing to check is that if you do one of these three operations that we talk about, they do not change the row rank, so they do not change the dimension of the set of rows viewed as vectors, or the dimension of the set of columns. Okay. I mean, for the set of rows, it's easier to see. You have if you think of each row as a vector, if you have a vector, or if you have a bunch of vectors, you change the order of two of them. That doesn't change the dimension of the span. Sorry. And similarly, so seeing it for the columns requires a little more thought, but not much. And similarly for the other operations, if you take a vector multiplied by a non-zero number, it doesn't change the dimension of your space. But once you prove that set of the elementary row operations do not change row rank or column rank, this kind of has a nice outcome. It shows that for any matrix, the row rank is equal to the column rank. Okay. Well, okay. Technically, it requires a couple more things. One is to check that using elementary row operations, you can always get to row reduced form. And row reduced form has these three properties. You can check that if any one of them is violated, you can remedy that using row reduced form, and you can use this to argue that you can always bring a matrix into row reduced form. And secondly, row rank and column rank are in some sense obviously equal for a matrix in row reduced form, but elementary row operations never changed either of them, so they must have been equal for the starting matrix, and so that gives you a proof that row rank is equal to column rank. In homework 1, I think maybe I don't remember if we had that problem proving it using adjoints, but this is an easier proof, of course, which is sort of just using things we might have seen in high school or college. Just as a quick check, in the matrix we developed, what is the row rank, which should also be the column rank by what we argued, but so if you think of these rows as vectors, what is the dimension of this column space, or how many linearly independent vectors can you have?
It would be 3, right?
It would be 3, exactly. So first of all, it's a span of 3 vectors, so the dimension can be at most 3, and it's equal to 3 because the 3 vectors are linearly independent because, well, they have these entries in different positions, and no linear combination can cancel out these entries. So you cannot write the first vector as a linear combination of the second 2 because the first entry will always be 0 if you take a linear combination of the second 2. Similarly for others. So the rank, row rank, that's what I mean by saying the row rank is kind of obviously 3 here, because there are these very clear entries which are just not present in the other rows, and so you cannot express them as a linear combination of the other rows. The same is true for columns. So there are the same entries. The first one is present only in the first column, the second one is present only in the second column, and so on. So you cannot write the first 3 columns as a linear combination, or sort of one of them as a linear combination of the other 2. So the 3 columns are linearly independent, and so the column rank is at least 3, can be at most 3 because these columns live inside R3, which is a 3-dimensional space. So so the row rank and the column rank of this is obviously 3 because of these disjoint entries, and I claim that this is always true for a matrix in row reduced form. I mean, not that it's always 3, but whatever is the appropriate number, these 2 are equal, and you can check why. And the third thing to notice is that we didn't really use anything about the field in defining all we did. All we said was the leading entry is 1. The element 1 is the multiplicative identity present in any field. Sort of some entries are 0, which is whatever is the lower triangle, sort of box to the left of the leading entry in a row. 0 is an element present in any field. It's the additive identity. And the operations we defined were you multiply a vector by a scalar, and if you have any matrix with entries in any field of your choice, the rows and columns of this form vectors over the same field, and you can multiply vectors by scalars. So sort of the rows and columns are both vector spaces of the form f to the n over the field f for any field f. So this procedure gives us a way of solving linear equations over any field, solving for variables over any field. There's nothing special about real numbers or complex numbers. We didn't use anything like inner products, etc. And so this is just generic linear algebra over anything. Any questions? Okay, so this is the kind of method which we might use when we are solving linear equations by hand, hopefully not too many of them. And the problem is it's not a very useful method to implement on a computer because it's actually quite slow. And if you think about it, every time you did an elementary row or column operation, you had to do something like, if let's say the matrix was square or almost square, so it had n+1 columns, n rows, one for accounting for one extra column of right sides. Every row operation required kind of subtracting roughly n entries from n entries, or sort of multiplying n entries by a scalar. So every time we did this operation, it cost us every time we did this elementary row thing, it cost us n arithmetic operations. And suppose you wanted to kind of eliminate the first variable, you would subtract the first row from everything. This would cost us n square operations, because you have to subtract the first row from the second one, first row from the third one, and so on. So you have to subtract the first row from n-1 other rows. Each of them takes n operations, so it's n square operations roughly. And naively, if you kind of eliminate the second variable and go this way, it will take another n square operations, so order n square. And if you keep repeating this, it can take order n cube operations in the worst case. And I mean, yeah, we can make all this formal, but for matrices of size n, this is not desirable. And so what we will actually talk about is methods for solving systems of linear equations much faster. But the downside is that they will only solve them approximately. So we'll not necessarily get an exact solution. We'll get a solution with some error, and then we'll see what is the notion of what does it mean that there is a little bit of an error in the solution to a linear equation. Okay. So before we kind of talk more about this method, let me just say, what is it that we are shooting for in terms of running time? So in some sense, the best we can hope to do, I mean, yeah, this is not necessarily formal, but suppose I gave you an equation, sort of gave you a solution, I gave you x and said x is a valid solution. To check that x is a valid solution, what you would need to do is multiply the matrix, let's say A0 here with x, and check if the answer comes out to be B0. So what you will need to do is matrix vector multiplication. And so that is the running time we are aiming for, or that's the gold standard. So to solve equations in time no longer than what it takes to check a solution. Okay? And check a solution here we think of as matrix vector multiplication. So and we will compare our running times to how long does it take to do a matrix vector multiplication. In the worst case, it can take up to n square arithmetic operations. If you have an n times n matrix, you kind of read every entry of it, multiply it with the corresponding entry of the vector. So it can take order n square arithmetic operations, which is already better than n cube. But it can be much less. So it can be if the matrix has only let's say s non-zero entries, and you are given the matrix in a way that you can access these non-zero entries in a random manner or directly. I mean, random manner, I just mean random access memory types. So then you can solve the matrix vector multiplication in time which is order s plus n, because you have to write down this output vector. So in particular, when s is n squared, this sort of is just what we said earlier. But a lot of the time, matrices arising in practice are sparse. So maybe every row has some 10 non-zero entries. So the total number of non-zero entries is 10 times n. Or in general, at least the total number of non-zero entries in the matrix are small, because these represent some sort of physical systems where maybe one variable is influenced by a small number of other variables, and you have a large system of variables, but it's not that everything influences everything. So there is some sort of limited interactions which govern the sparsity of this matrix. So
Is there no sparse structure for the vector x?
I'm sorry?
Is x not supposed to be sparse? It can be dense.
No, we are not assuming that right now. X is arbitrary. Yeah, so when X in addition is sparse, you can do something else that was sort of, we referred to it briefly in this compressed sensing kind of discussion last time, but today we're not assuming anything for X. X is arbitrary. And I mean, the matrix is also arbitrary. We are just trying to shoot for a running time, which is comparable to a matrix vector multiplication, whatever that happens to be for a matrix. We'll not use the sparsity of the matrix in any way in our algorithm. We'll just try to design an algorithm which only does matrix vector multiplications, and then if the matrix is sparse, we will get an advantage. Okay. Does that answer the question?
Yeah.
Okay. All right. So we will kind of phrase the problem in a slightly different way, just because it will be convenient to work with matrices in a specific form. So suppose we are given a matrix which is A0, our linear system is A0, x is equal to B0, where B0 is on the right hand side. Let's multiply it with A0 transpose on both sides. And if we are assuming that A0 is invertible, and by invertible, I mean that there exists a matrix A inverse or M, which when you kind of multiply on the left or right, you get the identity matrix. For this, A0 will have to be a square matrix. So let's say it's real entries, it's a square matrix. Then A0 transpose times A0 is also a matrix with which is a square matrix, etc. What I'll ask you to check is, okay, before we go there, let's rename things a little bit. Let's call this A. Oh, sorry, I forgot X. So, call this matrix A. X is what it was. And let's call this as B. Okay, so we started with this A0x is equal to B0. We obtained a new system. These are called linear systems. AX equals B. But now this A is of a special form. It's A0 transpose times A0, where A0 was our previous matrix. And you can check that if A0 is invertible, then we have a nice property that A0 transpose A0 is positive definite. So it is a self-adjoint linear transformation or a symmetric matrix with the real entries in this case, such that the Rayleigh quotients are always positive or all eigenvalues are greater than 0, whichever way of, and we saw a few different ways of thinking about positive semi-definite or positive definite matrices. Okay, so that's something I'll ask you to check as an exercise. So we will be solving, in particular, we will think of our system as AX equals B for A, which is positive definite. We can think of it as coming from this system A0x equals B0, which we will use for intuition, but we will not need to know necessarily know A0 and B0 for, well, okay, I take that back. So one thing, in addition, we can say is that if you can do a fast matrix vector multiplication for A0, then you can also do that for an A0 transpose, then you can also do it for A. So if you want to multiply A times X, you can first multiply A0 with X, and then if you can do this fast and do this fast, then you can also obtain a fast matrix vector multiplication for A times X. So it's possible that A0 is sparse, but A0 transpose times A0 is not, or A is not sparse. That's not a problem. If A0 admitted fast matrix vector multiplications, then A will too. Okay. A0 and A0 transpose both did. Okay. And sparsity is one way of this can happen, but whatever, if there is another algorithm, then you can also do this for A. And so in particular, we will think of how many matrix vector multiplications we need for our new matrix A, which we will think of as a positive definite matrix. And I'll sort of refer to this matrix A0 a couple of times just for intuition, but the algorithm will be just stated in terms of this matrix A. Okay. Any questions about the objective or the plan of what we are trying to do? So these iterative methods which start with some guess for a solution and then slowly refine it. And the way you kind of refine it is by thinking of the question of solving a system of linear equations as a question about minimizing, let's say, the error, which is just the norm of A0x minus B0. So how far is A0x from B0 if I'm thinking of both of them as vectors in R to the n in this case, let's say under the standard inner product, although we will see that you can also think of it as a different inner product. Okay, so instead of thinking about solving the system of linear equations, I'll try to think about minimizing this function. Of course, if there is a two solution x such that A0x is equal to B0, f of x will be 0. So the true optimum will be 0. But I will try to think of an algorithm which will try to get as close to the true optimum as possible, rather than in one shot trying to find the sort of solution where f of x is 0. Okay. And this is a special case of so-called convex functions. We'll see more about them later, but this is just sort of a quadratic function. You can think of the case when the dimension is 1. So you just have a quadratic function A0 times z minus B0, where z is just a single scalar variable. And you can plot this function on this kind of a parabola. And one way of minimizing it, which is called gradient descent or steepest descent, is what we will also use to solve these linear equations, is that you look at a point and then try to look at the tangent, because the function is decreasing in the direction of the tangent. Of course, so you take a step in the direction of the tangent, so you change your x a little bit, go in the direction of the tangent or the gradient of this function f. And you do this repeatedly. So you take maybe a small step and then you look at the gradient in this point, and you take another step and so on. And if your step size is not too large, you will come somewhere close to the optimizing point, and then we'll see a version of this or some proof of this in the case of linear equations. But you will get somewhat close to the true optimum, although depending on your step size, it's possible that you maybe overshoot it or are kind of nearby somewhere and don't quite get exactly to the point. This is the so-called gradient descent procedure for minimizing convex functions, and maybe you have seen this in some generality already. But to recap the method for our specific setting, let me just say what we would do in case of scalar functions. So the gradient or the direction of the tangent can be written just by, in this case, differentiating in case of a vector, differentiating according to every coordinate of the vector. And so you will get a vector of derivatives, which is the gradient vector. In case of a scalar, it's a single scalar, and you would maybe, let's say, take the new point, which is the old point, and step in the direction of the negative gradient in this case, because we want to decrease the value of the function. Okay, so let's say, let me denote some multiple, let's say eta over 2 times a0 z minus b. Okay, so I just wrote eta over 2 so that this 2 in front cancels out, and I get a clean expression of zt plus 1 is equal to zt minus eta times whatever is the expression giving the gradient in terms of a0 and b0 up to a factor of 2. And the same can be done, and in fact I can absorb this also. Actually, maybe let me not do it. So let me write it as eta times a0 square times z minus a0b. For our system of linear equations, this will become xt plus 1 is equal to xt minus eta times a0 transpose a0 minus a0 transpose b. Sorry, let's forget this. Times xt minus a0b, or which can be just rewritten as xt minus eta times 8 times xt minus b. This must be 0. Okay, just because a0 times b0, a0 transpose times b0 is what we call b, and a0 transpose times a0 is what we call a. So this is just the procedure we will work with. Okay. Any questions about the definition of the procedure? One other thing to notice is that at every step, all we need to do is a matrix vector multiplication. We need to multiply the matrix A with the vector xt, and then maybe subtract a bunch of vectors, which is order n, so it's no costlier than a matrix vector multiplication. And the question is, how many times do we need to repeat this process? And what is the guarantee we can get at the end, sort of after sufficiently many steps of this? Okay, so we'll discuss a couple of methods. In both cases, you sort of iteratively work with your matrix and try to get closer and closer to the true solution. One thing which I want to remark is that you can think of this optimum in another way, which is so let's say the true solution. So let's say a x star is a point such that a0 x star is equal to b0. So what we have is the norm of a0 x minus a0 x star, which is just the inner product of a0 x minus x star times a0 x where I'm using the standard inner product over Rn. But you can write this by moving the adjoint of a0 or a0 transpose to a different side and write this as x minus x star, or maybe actually, let me move it to the other. Now this is a positive definite matrix. We assume that A was positive definite, or equivalently A0 was invertible, which by the way also means that the solution is unique. Again, you can check why invertibility means that. So another way of viewing what we are minimizing is just the distance to x star under this new inner product, where we define the inner product of x and y as x transpose ay, or rather the standard inner product in Rn of x and ay. This is the new inner product denoted by, you've already seen this in the second homework, that if you have a positive definite operator, you can sort of evaluate it on one of the inputs, and that defines a new inner product. And you've seen some properties of this inner product. Okay, good. So there is a question about, is it possible to accelerate this? And yeah, we will see actually an acceleration of this process using what's called the conjugate gradient method. So we'll get to that in a minute. I'm just trying to define this slowly. But yes, there is an accelerated way of doing this, which is what is actually used in practice. Okay. Any questions? Any other questions? Okay, so as before, let's say x star is a solution which satisfies a times x star is equal to b, or equivalently a0 times x star is equal to b0, whichever way you want to think of it. And we define this iteration as xt plus 1 is equal to xt minus eta times axt minus b. So you can sort of write this in a convenient form by writing b as a times x star. So and subtracting x star from both sides, we get so this kind of has a nice interpretation that if you think of how far xt plus 1 is from x star, you can write it as this matrix identity minus eta times a times xt minus x star. Okay. And by induction, you can show that if you start with a point x0, then you have x0 minus x star, x1 is I minus eta a times x1 minus x star. And you keep repeating this by induction, you get that the tth point sort of minus x star can be written as this matrix identity minus eta a to the power t times x0 minus x star. Okay, so all we are doing is starting with some point x0. Without knowing what x star is, we are just multiplying x0 minus x star by this matrix I minus eta a to the power t to get xt minus x star. It's important that the operations we are doing are these where we only need to know b, we don't quite need to know what x star is. So they're kind of getting, or we are sort of multiplying x0 minus x star by this matrix without really knowing what x star is. And the question is, does this operation get us any closer to x star than x0 was initially? Any questions? Okay, so now let's try to think about if we get any closer to X star doing this sort of operation. So we use the definition of spectral norm of a matrix that we defined 2 lectures ago, that for a matrix, we take the 2 norm to be the maximum over a non-zero vector. The norm of what you get divided by the norm of what you started with. So in particular, what you started with was x0 minus x star. What you got was xt minus x star after multiplying with this matrix identity minus eta a to the power t. So we can say, just using the property or the definition of the spectral norm, that your distance from xt minus x star is at most the spectral norm times the distance of x0 and x star, or whatever you started with. And so if this is small, then we get closer and closer to X star. In particular, we'll also see how this changes with T. Any questions about this estimate? This is just sort of writing down the definition of spectral norm. Okay, so now let's get down to understanding what this term is or what it looks like, which is the convergence analysis. So let's say A has eigenvalues lambda 1, lambda 2, and as usual, we'll arrange them in descending order. Since it's positive definite, we know that all eigenvalues are greater than 0, and let's say we just call them lambda 1 to lambda n. Okay. What are the eigenvalues of identity minus eta times A? Actually, let's, okay. Yes, so 1 minus eta times lambda I. So the eigenvalues of eta A are eta times lambda I multiplied by a scalar. The eigenvalues get multiplied, you can check. And identity matrix has all eigenvalues 1, and in fact, any vector is an eigenvector. So in particular, eigenvectors of eta A are also eigenvectors of I minus eta A with the eigenvalues 1 minus eta times lambda 1, 1 minus eta times lambda 2, and so on. But now the order gets reversed because the lambdas were positive and you're thinking of eta as a positive number. So the order gets reversed. You can also check that the eigenvalues for a matrix M to the T are just the original eigenvalues to the power T. So the eigenvalues for this are okay. What is the order of these?
It depends on eta.
Right. So it really depends on eta because these things could be negative or positive. T could be odd or even. So the order can, I mean, the previous line, we always know that the order will be increasing. But now when we take a power, it really depends on whether we are taking the power of a negative number or a positive number. And that really depends on eta and also whether the power is odd or even. Okay. So here we don't quite know the order. Okay. But what we can say is that the maximum one in absolute value will be one of these. Because, I mean, you have just n numbers. which are in increasing order. So the maximum one in absolute value will be one of the endpoints. Either the most negative one will be largest in absolute value or the most positive one. And so when you take the tth power, it's still, you just raise absolute values to the tth power. So the maximum one in absolute value will be one of the extremes. We don't quite know the order. And this we can state more conveniently as the fact that the spectral norm, which you can check that for a symmetric matrix or a self-adjoint operator, it's the maximum of the largest and the smallest eigenvalue. So it will be one of the two endpoints, and I will leave this as an exercise. So we are interested in one of the two endpoints, and we want to choose the eta in such a way that the maximum of the two endpoints is still small. I mean, and we can forget about the tth power if we are just thinking about the absolute values. So we just want to make sure that 1 minus eta times lambda 1 absolute value and 1 minus eta times lambda n absolute value are both small. So let's plot them. Okay, and this sort of red and blue curves are the absolute value of 1 minus lambda times theta 1 and 1 minus lambda times theta n in absolute value. And what we want is an eta such that the maximum of the two curves, or whichever is higher, is still not too large. And the best point to choose is this one, where both curves meet, because when they're not meeting, one of them will be higher than the other. So the maximum will be minimized at the point when so eta 1 is larger, which means that the slope of the blue curve is larger. So here we are looking at eta times lambda 1 minus 1 is equal to 1 minus eta times lambda n. And if we solve for it, we can choose eta to be 2 over lambda 1 plus lambda n. Okay. So this is a choice of eta which will minimize the spectral norm of the matrix identity minus eta times a to the t. And we'll see what that means in terms of how close we get to the objective, but that's what the minimizer will be. Okay. Any questions about this computation? Okay, so let's plug that in, and I've done a few simplifications using these values. So we chose eta so that the two endpoints have equal absolute values, so we can use any one of them. I'm just using 1 minus eta n to the t as the spectral norm, and both this and the absolute value of 1 minus eta times lambda 1b will be equal because of our choice. And here, let me write it in a slightly more convenient form, just plugging in the value and then writing it in terms of the ratio of lambda 1 and lambda n, which is for a positive definite matrix, or even for other matrices, but you have to define it slightly more carefully. It's called kappa, or the condition number of the matrix. And the so what we got was the spectral norm is roughly 1 minus something like 1 over kappa to the t. Kappa is a number which is bigger than 1. It's the ratio of the largest eigenvalue to the smallest for positive eigenvalues. And so we get that we are pretty close to the starting point, or sort of the optimal point, if t is large enough. And here you can take logs on both sides and check that it suffices to take t to be roughly order kappa times log 1 over epsilon. So t is the number of times we are kind of doing this iteration, the number of times we are solving it. Okay, there's a question in chat. Let's see. Good. So how do we choose eta in advance? Right. So here we are saying we have kind of eta, an expression for eta in terms of lambda 1 and lambda n. You're right that we may not always have the knowledge of the values of lambda 1 and lambda n. So one answer could be, yeah, if you have some estimates on what the ratio of lambda 1 and lambda n are, or if you know some estimate on the condition number, you can choose eta accordingly. Actually, we'll see another method where you don't need to choose eta, and we'll reinterpret this in a different way. And all we need to do is kind of to find the point xt, but writing it in a different way will not need to know the value of eta. But otherwise, yeah, in this setup, you will need to know at least some estimate on the condition number to figure out a value of eta. You can show that you don't need to know exactly the lambda values of lambda 1 and lambda n. And if you know some bounds on, then you can still choose eta. But some knowledge is required, at least for this method as well. I mean, the same is true, for example, when you're trying to choose step size in certain applications, you need to know something to use the optimal step size. But yeah, here, at least as stated, we'll need to know some estimates on the condition, but we'll remedy that in a moment. That's a good question. Okay, now, as an exercise, yeah, I mean, you can check that t equals this kappa times log 1 over epsilon suffices. And recall that we were doing sort of each iteration required a matrix vector multiplication. So what we are doing is roughly kappa times log 1 over epsilon matrix vector multiplications. So the running time is basically kappa times our gold standard. Think of epsilon as some small constant, let's say 0.1. So log 1 over epsilon is some constant. And what we are, but I mean, yeah, you can also think of in terms of epsilon as a parameter if you like. And this is roughly the cost we pay in terms of the gold standard of operations. And we'll see that this can be sped up. And in fact, the optimal thing to do only requires square root of kappa iterations rather than kappa. And we'll get to that in a minute. Another thing to check as an exercise is that we defined this other distance, which was according to this inner product defined by the positive definite matrix A. And what we said also works in that distance instead of the distance in the L2 norm. And for some applications, really, because we are looking at xt and x star as solutions to ax equals b, the distance as sort of governed by the inner product of the matrix A is really what matters in some applications. So you can also obtain same bounds for those kind of things. Okay. All right. Let's take maybe a 2-minute break, and then we can continue. And I'll show you how to speed up this method a little. Okay, any questions that you thought of? Okay, so now let's get to a method which is actually used in practice, and this answers some of the questions that were asked earlier. This is in some sense an acceleration of the gradient descent or the steepest descent method. It's also a method where we will not need to know the condition number in advance or choose this eta, but we'll write what we are doing in a slightly different way, and we'll see how to compute with that. Okay. So the starting point is the observation of what happens if we run our previous method. And let's say, for convenience, let's start with x0 equals 0. And let's see what are the points that we obtain as we run this process. So x1 is x0 minus eta times a times x0 minus b. x0 is 0, so you just get eta times b. x2 is, again, you can check, but it's something like 2 eta b minus eta squared times a times b. And I think what I have for x3 is correct, but yeah, maybe I made a mistake in the computation, so you can check that. But what I do know, and you can prove by a simple induction, is that in our process, we always obtain xt, which is a linear combination of the vectors b, a times b, a square times b, all the way up to a to the t minus 1 times b. xt is always some linear combination of these vectors, or it's in the span of these vectors. Okay. So we'll forget about how we obtained a vector in the span and just remember this fact that we obtained something in the span of these vectors. The span of these vectors, starting with a matrix A and a vector B, or a vector B in a linear transformation given by A, has a name. It's called the Krylov space, or KTA, B, or the Krylov, so-called Krylov space of dimension at most t in this case, because we are looking at a linear combination of t vectors, and you can think of t as a parameter and define many spaces like this. So we are always looking at xt, which is in the span of some vectors like this. And so the conjugate gradient method can be thought of as just finding the best vector in this span. Okay? Forget about etas, forget about this iterative application, just at every step, increase the value of t by 1, so the space becomes larger. It's the linear combination of one more vector. So xt will just be the minimizer in this space. This is some vector space. It's the span of vectors b, a times b, all the way to a to the t minus 1 times b. Okay. And the goal is just to find the minimizer of f of x in this space. And we'll not worry about sort of writing it in terms of these etas, etc. We'll just look at this space, which is defined by this a and b, and just find the minimizer. Okay. All right. So, I mean, in particular, it's doing at least as well as the previous method, because the previous method was constructing some very special linear combinations in this space. Now we claim that we will shoot for the best linear combination. So we'll just kind of take this intuition of being in the span and just run with it. Okay. Any questions about what we want to do? Okay. And this is a question which we actually also have seen before. So remember, we want to look at f of x as a distance, and I claim that you can think of it as a distance under this inner product defined by this matrix A. So what we are trying to say is that we are trying to find the closest point to x star in the subspace k sub t of a comma b under some inner product, under some distance defined by this inner product corresponding to A. And this is something which we saw when we were doing least squares approximation. We saw how to find the closest point to some given x star in a subspace. Okay. In particular, if we have an orthonormal basis for this subspace, then an orthonormal under whatever inner product we are interested in, then the closest point to x star is just copy the coefficients of all the vectors which form an orthonormal basis for this space. And so this is the orthonormal projection to this space under the inner product given by this matrix A. Okay. This is sort of exactly the same computation we did in terms of finding closest point to sort of in a subspace S, finding a closest point to a vector V, which is not necessarily in S, but finding the projection to S.
How do you know the dimension of Krylov subspace is T?
Great. So I don't necessarily know. Here I'm kind of stating it's at most T. So I wrote down T vectors, but otherwise we find an orthonormal basis and it will have the right number of vectors. So yeah, you're right that I don't know it's exactly T. Okay.
So Wi are not necessarily orthonormal?
No, I will have fewer than, so I will have W1 to Wj for j less than equal to T. Whatever is the right number, I will have that many, and we'll see how to compute this orthonormal basis. But yeah, I intend to have whatever is the right number of orthonormal vectors equal to the dimension. Okay. Does that answer the question?
Yeah.
Okay. So suppose I know the dimension and suppose I have the right number of vectors which form an orthonormal basis for this space. Then I can compute the closest point to x star in terms of these orthonormal basis vectors, where the coefficients ci's are just the inner products of wi with x star. Now, of course, I don't know x star, but I still know how to compute this inner product because this is defined as wi inner product A with x star, which is just inner product of wi with B under the standard inner product on Rn. Right? So I know how to compute these coefficients even if I don't know x star, because this inner product requires a multiplication by A, and I know A times x star. Okay. So my claim is once I know an orthonormal basis for the Krylov space, I can solve this problem of finding the closest point to x star in this space. And I mean, so far there is no iteration. I just said that for any t, if I know a basis for k sub t, then I can find x sub t. Okay. Just because I know the right coefficients to choose. Any questions about that?
You know the right coefficients to choose, so you can get the linear combination with wi's.
Mm-hmm.
How does the xt that you get is the minimum of x minus x star?
Well, it is the minimum because we kind of saw this that if you have any space S and if you have any inner product, in this case this inner product defined by this matrix A, then for any vector V, so for any vector V, we can, not necessarily in S, we can find the closest point in the subspace S. And the way we find the closest point is that let's start with the basis for S, complete it to a basis for the whole space. And then V can be written in terms of this entire basis for the entire space. And the way you find the closest point in S is just by taking the part corresponding to W1 to Wt and deleting all the rest. So the closest point this is the closest point where you only go up to T rather than D.
Oh yeah, so okay. Xt is the projection of x star onto
Xt is the projection of x star, so it is the closest point to x star under this notion of distance given by the inner product for A, which is what I'm working with anyway.
Yeah.
Okay, good. So I know how to find the closest point to x star. So yeah, you're right that I will initiate this with V as x star. And the subspace S will be the Krylov space. Okay, so what I need to do is to be able to find an orthonormal basis, and of course also find the right number of vectors. So the basis will also tell me the dimension. Okay, this actually is what is done iteratively. So this is the iterative part. And it's basically Gram-Schmidt under this inner product, is under this funky inner product defined by this positive definite matrix A. So it's Gram-Schmidt under the general inner product. And naively, Gram-Schmidt would take you kind of T square operations if you are looking at a T-dimensional space, and that will kind of kill any advantage we might obtain in terms of T as order sort of the square root of kappa. But I will kind of break this down into pieces and put it as an optional problem in the third homework, so you can see how to compute this orthonormal basis fast. It can be done in order T time. And that's what we will really need to implement the algorithm. And this, I mean, yeah, I will break it down into parts and put it as a homework problem, although it will be optional, I think. I'll make this optional. So you can do this if you want to just see how this works. Just quickly going to
one question. It doesn't depend on the dimension of Wi's. So N only order T.
No. It will require order T matrix vector multiplications.
Oh.
So I'm stating in terms of iterations or in terms of how many matrix vector multiplications I need. The time for a matrix vector multiplication, it is dependent on the dimension and the non-zero entries in A. So it will require sort of order T multiplications of a vector with the matrix A. Does that answer your question?
Yeah.
Okay, good. So this, you can see.
So I don't know whether you covered this, but what is the dimension of the Krylov space?
What is the dimension of a Krylov space? So yeah, so here it's at most T, but I don't know exactly if it's exactly T or not. So I mean, Krylov space is defined as a span of T vectors. They may be all linearly independent, in which case the dimension will be exactly T, or maybe there is some dependency between A times B and so on. So maybe they are linearly dependent, in which case the dimension will be less than T. I claim that this process, which we'll see in the homework, will compute whatever is the right number of basis vectors and time, which is at most order T matrix vector multiplications. Okay, but yeah, I don't know a priori exactly what the dimension is. I just know it's at most T.
So just a sanity check. Let's say B is 10 dimensions and T is 1,000 steps.
Sorry, can you say that again?
So let's say B is 10 dimensional and T is 1,000 steps.
Oh, B is 10 dimensional, you mean? Then of course it won't be, because all these vectors are living in 10 dimensional space, B, A times B, and so on. So if I do 1,000 steps, of course the dimension, I mean, it's at most 1,000, but it's also at most 10, because the space is a subset of R to the 10. So yes, it will be the maximum of the dimension of B and T. Here, and in most applications, I'm interested in the case where the dimension n of the vectors of the ambient space is much larger than kappa or epsilon. Or so we are thinking of T as much smaller than the ambient dimension. So I mean, it's still true the dimension is at most T, but of course, if the ambient dimension, or if B lives in only 10 dimensional space, then the dimension of the Krylov space cannot be bigger than 10.
I guess it would make sense that following up on that, it would make sense that if you run for n steps, if you find the Krylov subspace of n steps, where n is the dimension of the problem, then the Krylov subspace will cover Rn.
Yes, in that it will cover Rn, and at that point the minimizer we are finding is the
whole minimizer.
Solution. Right. But what we are really interested in is how does it change if we are at a value of T which is much smaller than the ambient dimension. And even at that point, can we give some guarantees which get better with T? Maybe not all the way, maybe they're not exactly zero, but at least get smaller with T. Okay. Yeah, that's a good point. Anything else? Okay, so let me just, I won't do the full analysis, but let me quickly say that this can be analyzed pretty much in the same way we did before. So what we now know is that xt is some linear combination or some element of the Krylov space. So you can think of it as some polynomial in terms of A, which is some other matrix multiplied with the vector B. Okay. And so if you can also think of x star minus xt as identity minus right, you can think of B as A times x star. So you can write the whole thing as this identity minus PA times A times x star, which is just some other polynomial Q. So previously we had x star minus xt is identity minus eta A to the power t times x0 minus xt. Here we kind of started with x0 equals 0. So this is just x star minus x0. But this polynomial Q is something else. It's not identity minus eta A to the t, some other polynomial. But it still has the property that if you think of it as a polynomial in scalar variables, then Q of 0 is equal to 1. Because sort of A times P of A, if you think of it as x times P of x for a scalar variable x, then it's 0. And so you get identity, which is 1. And the values or how close we get to the true solution will be determined by the eigenvalues of this matrix Q of A. So you can check as before that the eigenvalues here will be just Q of lambda 1 to Q of lambda n. But we don't know the order. In particular, this is a polynomial. It can take different values at different points, and it may not always be increasing or decreasing. Okay, so we don't quite know what the values are. But you will still get the same sort of bound that if you know the spectral norm of this, which is the maximum eigenvalue and absolute value. So you can check that this will be the maximum value of the polynomial Q on one of these points, lambda 1 to lambda n in absolute value. And in some sense, Q is the best polynomial or sort of, you can, yeah, there's a little bit of argument, but you can show that Q is the best polynomial which minimizes this bound. And in particular, there is a polynomial which shows that the bound is not too large, or the bound can be written as roughly 1 minus square root of, sort of 1 minus 1 over square root kappa to the t. This requires proof, but these polynomials are sort of constructed from so-called Chebyshev polynomials. We don't need to know what they are. They're just needed in the analysis, but it shows that there is, in particular, the best Q will have a dependence of 1 minus 1 over root kappa. And then sort of the same analysis as before will tell you that square root of kappa iterations suffice roughly. The key part is implementing this question, this issue of finding an orthonormal basis, which I'll break down as a homework problem. I'll also write down some details of Chebyshev polynomials in the notes in case you want to take a look at it. But yeah, what we need is just this fact that some polynomial exists, which shows that the best polynomial Q will have small spectral norm. Okay, sorry about going over a few minutes. I'll stop here. I'll stay on. If you have any questions, feel free to ask me more. But yeah, I'll stop.